go. I'm taking your word, and it better be correct. All right, here we go. We are starting our new unit. Our new unit is on intermolecular forces and properties. What we've been talking about in the last chapter was intramolecular forces. So intra is between molecules, or between atoms in a molecule. Intermolecular forces then is going to be between molecules. Okay? So our first section is actually on intermolecular forces. Intermolecular forces then, we have attractions between atoms, ions, or molecules that hold them together. They're not chemically bound. They are attractions, but they're not chemical bonds, okay? There are 6 different types of IMFs, which we'll get to today in class. They differ in their arrangements of the electrons. They explain why CO2 is a gas, water is a liquid, and silicon dioxide is a solid at room temperature, even though they're made up from 3 atoms. Okay? To determine the type of IMFs, you have to look at the types of atoms that are there and start identifying, first of all, if they're metals or non-metals. All right, makes sense? So far, anything up there doesn't make sense so far. All right. So IMFs, we've got 3 different types of IMFs on here. And then the rest of these are, so these are different types. We've got London dispersion forces, which we abbreviate LDF. And that is a standard abbreviation that is allowed on the AP exam. Okay, so if you write LDF and you're talking about intermolecular forces, they will know what you're talking about, and you don't have to write out London dispersion forces. IMFs then are intermolecular forces, and you may abbreviate that on the AP exam as IMF to avoid having to write out all that mess, because you're trying to save time. So IMF is intermolecular forces. London dispersion forces are our first type. Then we have 2 types of dipole-dipole. We have one that's just called dipole-dipole. And then we have a special type of that that's called hydrogen bonding. It is not a bond in the traditional sense of a word. We don't really like the fact that they call it a bond, because that makes you think of intramolecular forces, and this is not intramolecular, okay? So it's not between atoms, it's between molecules. So that word bonding here is not the best choice of words, but that's what they gave us, and that's what we have to work with, okay? Then we have ionic between metals and non-metals. We have metallic, which applies to only metal atoms, and then we have covalent network. And we'll get into all of these and talk about them specifically. So London dispersion forces occur in substances where if there is only one type of IMF, then it's a nonpolar molecule. So everything out in the world has London dispersion forces. Everything. London dispersion forces are caused by the motion of electrons in atoms or molecules. As the electrons move around the atom, there's a chance, just because of their movement, that you're going to end up with one side that has more electrons than the other. When that happens, that is called a temporary dipole. Okay, so I tell people to kind of think of it like water. Okay, if I have a glass of water, it's pretty easy for me to walk across the room with a glass of water, right? It's going to be wobbling a little bit in there. But if I have a big old tub of water and I'm trying to walk across the room with that, right, it's going to slosh more. So the more electrons you have, the higher the LDFs are going to be. because there's more of a tendency for them to end up on one side or the other. But it's just temporary, because remember, these electrons are constantly in motion. So it's just a temporary dipole. It's not there permanently. But this exists in everything. If you have a nonpolar substance, the only IMF you're dealing with, though, is London dispersion forces. That's it. That's the only thing. We can also have what's called an induced dipole when a neighboring species gets close. And so when one of them has this shift and they've got an end here, then they get close to something else, and that's going to cause a shift in the next one. So because I've got a shift in my electrons, and this end's positive and this is negative, if I get close to Lily, all of a sudden this positive end, her negatives are going to come on her side, towards me. That side's going to be negative and that side's going to be positive. And then Li Ming is going to have, and it's going to continue around. And you're going to induce, I induced a dipole in you, you're going to induce a dipole in him, and keep going around. Okay? So this is what we're talking about. We get that bunching. So this would be kind of like my positive end. And then I'm going to induce a dipole in Lily, and she's going to do this. And then she's going to induce Li Ming, and then so forth and so on as it carries her. But it's temporary, because my electrons are constantly shifting, and they're eventually going to go back to this, and then that dipole is going to disappear. And then hers will, and his will. And yeah. So it's very temporary, because these electrons are constantly flying around. All right, ability of an atom to form this temporary or induced dipole is called polarizability. They love this term. Okay, so if you have your pretty little highlighter out, or you want to take your pencil or whatever, they love this word. This is one of their pet words, just like when we were dealing in chapter 1, and they like the Coulombic attraction idea. Okay. Effective nuclear charge was another pet term that they loved. This is another one. They love polarizability. Okay. So London dispersion forces are stronger when an atom or electron or molecule has more electrons. This is going to show particularly well when we look at these diatomics here on the periodic table with our halogens. They change in state going from a gas to a liquid to a solid. So if you look at fluorine, fluorine is bonded to another fluorine. It is a gas at room temperature. Chlorine is the same thing. When we get to bromine, though, it is a liquid at room temperature. And when we get to iodine, it is actually a solid at room temperature. Yep. As we move down, we are increasing electrons. And that makes this more polarizable. Okay? So because we've increased the electrons, there's more electrons in iodine than bromine. Iodine is more polarizable. And again, they love that term. Absolutely love it. They eat it up. All right. Another factor that deals with this is the strength of the London dispersion forces is the shape of the molecule. Long, thin molecules have more surface area and are more polarizable than short, round molecules. And again, if we go back to my glass analogy, if I've got a tube of water that I'm carrying down, okay, and it's, you know, kind of round and everything, I can kind of keep that water in play. But if I have a long, skinny tub of it and I'm trying to walk across the room, there's a pretty good likelihood, especially with me being as klutzy as I am, that water is going to slosh out. Okay. These long, thin molecules, there's more there's more surface area, so they're more polarizable. The less surface area you have, the less polarizable it is. The more surface area you have, the more polarizable it is. The more polarizable, the stronger the LDF. Yes?
Would the longer, thinner molecules be chain?
Yep. So let me see. Yeah, stuff like, and that is primarily, yeah, that's a good analogy, is the chains. So you know how you've got fat, and fat is nonpolar, right? Okay, but it's a solid at room temperature. The reason why it's a solid at room temperature is because it's those long chains of hydrogen and carbon bonds that are made, and those long chains then become more polarizable. So if you look at a lipid molecule, okay, the lipid molecule has these long chains of hydrogen-carbon bonds. Those become more polarizable. And because of that, that allows that liquid to, or that oil to be a solid at room temperature. The longer the chain that is, the more likely that is to be a solid versus a liquid. And that's why you've got a nonpolar molecule that's still a solid at room temperature, because that's not typical. A good portion of your nonpolar molecules end up being liquids or gases at room temperature. But fats are an exception. It's because of that long chain, there's long chains of fatty acids there. Okay. And again, the LDFs can also be enhanced by pi bonding, the presence of double and triple bonds. All right, LDFs then exist between all atoms and molecules. So when they ask you what IMFs are present in a substance, the first thing you write down is LDF. You don't think about it. You don't acknowledge it, because it's going to be there. Okay? It's going to have LDF. It may not have the other stuff, but it's going to have that, darn it. Okay? So make sure that you get that one down. It will. It'll be there. Again, they're going to increase with surface area. It's going to make it more polarizable. Polarizability, in turn, increases with number of electrons. And we talked about that. That gives it more, essentially, water to slosh back and forth. It gives you more electrons to make it more polarizable. In short, larger molecules with larger surface areas have more electrons, so they're more polarizable. This leads to more London dispersion forces and greater attractions, and that is manifested in higher boiling points. You can look at, if you're comparing molecule 1 to molecule 2, and this has a higher boiling point, that equals higher IMFs. The IMFs are what determines your boiling point. When you boil something, you're getting rid of these IMFs. They're gone. These are what holds it together as a liquid. And they hold it together even tighter as a solid. So when you go from solid to liquid to gas, you are reducing. So this way, when you're going from here to here, you are reducing IMFs. And in theory, if you have an ideal gas, okay, which we'll talk about in section 4 of this unit, if you have an ideal gas, it has no IMFs. Yes, sir.
Are those the ones where one up and then it would say when the change of state is like straight line?
Yep. So that is a heating and cooling curve, which I think I have on one of these slides coming up in like days. But when we look at a heating and cooling curve, when we go up like this is heating. This is your solid. Here is a phase change, because during a phase change, the temperature stays the same. So this is either melting or freezing, depending on which direction you're going. If you're going this way, you're melting. If you're going this way, you are freezing. Then we increase here. This is our liquid state. We get to a point here where we plateau. This is where we are going through vaporization if we're going through this way, or condensation if we're going this direction. And then eventually we get to the gas stage over here. Okay? So here you are reducing IMFs. Here you're getting rid of them completely if you're going this direction. If you're going back the other direction, here you're reestablishing IMFs, and here you're making them even stronger. The reason why something is a solid, liquid, or gas is the strength of its IMFs. That's what determines a solid, liquid, or gas.
I was going to say, could you explain why the temperature is constant?
Because all the energy that you're adding in when you're going this direction is going to get rid or reduce, in this case, reduce your IMFs. Here, it's going in to get rid of those IMFs altogether. And then when you're coming back the other direction during that phase change, that energy is going back into reestablishing IMFs here and strengthening them here. But it's kind of like a multitask kind of thing, you know, like it can only do one or the other. It can either like be a gas, or it can start to work on these IMFs, but it can't do both at the same time. Now, obviously, I'm personifying this, but you get the idea. Yeah, Ethan? Were you going to say something?
So when you're like boiling water, temperature stays the same.
Yep.
When it's evaporating.
Yep. When you go through that vaporization time, the temperature during a phase change, whatever phase change it is, the temperature of that substance is not changing. Okay? So if you look at water, for example, if you're going from the solid to a liquid with water, what temperature does water melt at? 30. Okay, we want to do Fahrenheit. That's fine. 32 degrees Fahrenheit. 0 Celsius. Okay, that's fine. Either one, I don't care. What temperature does water freeze at? 32 degrees Fahrenheit or 0 degrees Celsius. The difference is, are you pumping energy in to reduce the IMFs, or are you removing energy from that system to increase the IMFs?
Endothermic and exothermic?
Yep, endothermic and exothermic. If you are putting energy in to the system, it's endothermic. So melting is endothermic because we're adding energy in. Freezing is exothermic. Energy is getting out of that system. We're removing energy from the system. And we do that with a nice little device called a refrigerator or freezer. Okay? That's what those things do. They're just removing energy from that closed system, or what you hope is closed, because if it's not closed, you know, you're wasting a lot of energy. Make sense? Your fridge underneath feels warm. It's because of the heat of the motor, but it's also because it's removing energy from the food that you put in there. If you put warmer food in there, it's going to be removing that energy from that food. All right, does this make sense, what I've talked about up here? Does it make sense? Is it clicking for you so far? These IMFs are huge, though. Like the whole foundation of Unit 3 is built on these IMFs. So make sure, as I'm going through this, if you've got questions, we talk about it. Stop me, please. All right, so these are LDFs. Again, like I was saying, one of the manifestations can be found in these organic molecules. As the surface area increases, we can see that showing up in the boiling points. So for example, pentane here has a boiling point of 309 Kelvin. This guy, methylbutane, has is 301 Kelvin. They are essentially the same structure, but this one is longer. So if it's longer, it's more polarizable, which leads to it having a higher boiling point due to its increased IMFs. Okay, summary. Larger molecules, larger surface area, have more electrons because they are more polarizable. That leads to greater Ldfs, and therefore, as a consequence, higher boiling points. All, and I mean all, atoms and molecules exhibit LD.
So everything gets bigger. Like, I mean, for like the larger molecules, everything increases.
Right. So the bigger the molecule, the higher the IMFs due to London dispersion forces. Okay. There's going to be some other stuff that can be more significant, not always, but can be more significant. Okay. All right. Boiling points of noble gases here. If we look at these, okay, what is happening to this as we go across here? It's not, no, it's going up. This is a negative value. So we're getting closer to 0 as I go across here. What has happened to my number of electrons? Increasing. Increasing number of electrons equals more polarizability, leading to higher IMFs. Okay. Look at our halogens. Okay, we already did that. We've already kind of done this one. But you can see that their boiling points also increase. On descending group 18, the elements get bigger. They have more electrons, larger surface areas, leads to London dispersion forces between them, making them more difficult to separate and increasing their boiling points. Yeah.
Put into a solid state.
I think you can get it into a solid state. They have to change the pressure, it looks like, to get it to happen. Yeah. And it's close to 1 degree Kelvin. So under high pressure. But it looks like they've done it. So all right. Dipole-dipole interactions then are between molecules that have a permanent dipole. And you should be able to identify those now that you are done with Unit 2. Molecules are polar when their electron distribution is asymmetrical. It's always a good idea to sketch the molecule to determine if it's symmetrical or not. Dipole interactions are similar to London dispersion forces, except that the dipoles are permanent. And so the attractions are greater, generally greater. Okay. Now, sometimes you will see problems like where, like, for example, HF, okay, there's not a lot of electrons here, as opposed to, and this is a polar molecule, so this is going to have dipole-dipole, and it's going to have London dispersion forces in it. That is a liquid, okay, I believe it's a liquid at room temperature. Yeah, it's a liquid. Okay. I is only LDF. This is a nonpolar molecule. This is a solid. Okay. So the boiling point of this is higher than this, even though this has London dispersion forces and dipole-dipole. What is the difference between these two then? Right. This one has higher LDF, making it more polarizable, and therefore it's going to be a solid at room temperature as opposed to this guy. So when you get one of these anomalies where you're like, but this only has LDF, why would it be a solid? Go back and look at that LDF. There's something there. This guy is huge compared to this guy. Okay? How many electrons here? Well, we have 10 electrons here. Here we have, God, how many? 106. See the difference? It's a over 10-fold difference between these two. So that this guy's more polarizable, and it's the London dispersion forces. Okay. By and large, dipole-dipole will have higher IMFs versus LDF. Okay. But you will see some of these anomalies once in a while where you're like, what? It's the LDFs. Go back and look at the size of the thing. Yeah. What?
Does HF also have hydrogen bonding?
Yeah, but we haven't gotten there yet. So it does have hydrogen bonding as well. Matthew's getting ahead of me. I guess I should have used HCl. That would probably be better. So if I use HCl here, then that's going to give me my dipole-dipole and LDF, and then I can compare it. Better? It's still a liquid, although the electron count's going to go up a little bit. So that's going to take it up to 17. That would take it up to 18 electrons. But still, it's just the LDF at play for this one. All right. So when these things come into contact with them, again, this is intramolecular. This is a covalent bond here. This guy right here is going to be your LDF, because it's always LDF, and dipole-dipole. And a lot of times they will use a dashed line here and a solid line here. Why would they make this one dashed and this one solid? Yeah.
Because the solid ones are intramolecular.
Right. And what do we know about the strength of intermolecular versus intramolecular? Right. Intermolecular is not as strong as intramolecular. So it makes sense that this is dashed because it's not as strong as this guy. Okay. So in a 3D dimensional plane, the complete picture is a little more complicated. Molecules are going to come around in such a way that attractions are maximized and repulsions are minimized. Eventually it lines up so that we end up with that attraction and repulsion working out. So the molecules are going to kind of be like almost like magnets, where this one gets close and the positive one over here comes up, around, and the negative one here, there's going to be some repulsion here, but it's going to get attracted to the positive here, and you get kind of those attractions and repulsions going on. Generally speaking, the dipole-dipole is stronger than London dispersion forces. But again, just like in this example here, it's not always the case. So be careful. Tread lightly. Look at everything. Get all of the evidence and all of the facts. All right. Here is Matthew's hydrogen bonding that he wanted. And we are not getting out at 25. Remember, we're on that advisory schedule. We don't get out of here until 37. So I still got time with you. No packing up. Thinking about packing up. All right. Hydrogen bonding is confusing. Again, I don't like the word bond. It's not a bond. Okay. It's not a bond. It's an IMF. Okay. Not the best choice of words, but that's what science has named it. So we're going to have to just try to wrap our brain around it. It occurs in molecules that contain HN, HO, and HF. And we give it an acronym, phone. Is it on the phone? Does it have these bonds in it? Okay, now why does that work? Why is that the way it is? Well, remember, nitrogen, oxygen, and fluorine are the 3 most electronegative elements out there. Hydrogen only has 1 electron, and these guys end up being electron hogs. They essentially say, hey, hydrogen, you've got an extra electron. I want that. And that electron spends more of its time on this end of the molecule than it does over here. When that happens, this end ends up being positive, and this ends up being negative. Another molecule comes along, has the same situation. This ends up being negative, and this ends up being positive. And they get attracted to one another. This oxygen with this hydrogen, this positive with this negative. They're attracted to one another. That attraction is called a hydrogen bond. It is an IMF. If they ask you to write down the IMFs that are involved and you've got hydrogen bonding written down, you darn well better have two other ones written down as well. Dipole-dipole, and what does everything have? Okay, so if they ask you what types of IMFs are involved and it has hydrogen bonding, you better have these other two written down because you will not get all the points otherwise. Questions? Anything not make sense up here? Okay. Consequences then of hydrogen bonding. Substances, we're taking a mass break. Substances with hydrogen bonding typically have higher boiling points. They tend to be viscous. What does that mean? Thicker. Yeah, thicker. And if we were to drop it, it would take a longer time for that drop to fall. So they tend to be like maple syrup is viscous. Molasses. If you guys have ever had molasses, molasses are viscous. Water is not. Yeah, tar would be viscous. They are both are explained by the increased attraction of the molecules due to hydrogen bonding. The more difficult it is to separate the molecules, especially intermolecular forces, these large molecules, it makes it more viscous, and it's also going to give it higher boiling points and higher melting points. So here we've got to break down all of those forces in order to get this water to go into a gas state. If we look at these and we're increasing our Ldfs here with these, we're increasing our boiling points. These are all nonpolar. Now, if we look at this and instead of having these group 14, we move to group 15. So NH3, PH3, AS3, ASH3, and SBH3. Okay. As we move along here with these guys, our boiling point is going to increase. But here we've got kind of this weird anomaly. We would expect this guy to be what number? Minus or less than this guy, right? So negative 90, negative 100, something that is less than this value. But we've got this weird anomaly. So at that point, you need to look at this and go, oh, what? Why? Well, if we draw the molecule out, we will see that we have a hydrogen connected to a nitrogen, okay? And that hydrogen with that nitrogen here, nitrogen's going to be an electron hog. And that's going to cause this end to be what? negative, and this end is going to be positive. When another one of these comes along, then you're going to have your nitrogen here, and you're going to have that hydrogen bonding occurring between these two. Okay? If we take this out, and instead of having nitrogen here, it's going to have the same structure with the phosphorus, but this isn't going to be as great. Why? There's no hydrogen bonding here. This is phosphorus. Hydrogen bonding is only when you're on the phone, and that's a phone with an F, not a P. That would be a pone. This is a phone. Phone home, baby. All right. So here, if we look at group 16, again, we're increasing, we're increasing, we're increasing. Here we've got this anomaly. This is water, okay? And I mean, that's a huge difference. But it's because of the hydrogen bonding.
Why is it so much greater for oxygen than for nitrogen? Like the hydrogen.
I don't know. Again, another anomaly. You got to figure out why. And here's just kind of a graphical representation of that, what we just talked about. You can see here as we move down and up. You would expect this to be down here somewhere. You would expect this guy and this guy to be down here, like this is trending. Oh, mass breaks over. And yet it's not, and that is due to the hydrogen bonding. All right, naming interactions. If we have just nonpolar substance A and substance B is nonpolar, we're dealing with London dispersion forces. If we have two polar molecules, we're dealing with dipole-dipole and LDF. If we're dealing with polar and hydrogen bonding, polar with hydrogen bonding, we're dealing with hydrogen bonding, dipole-dipole, and LDF. If we have a nonpolar polar, we end up with a dipole-induced dipole. This dipole is going to induce a dipole in this guy. It's going to cause that to shift around. If we have an ion and a nonpolar substance, we're going to have an ion-induced dipole. Remember, ions are positive or negative charges. They're going to cause this to have an induced dipole. And then polar and ion is going to be an ion dipole. So this is kind of a nice handy chart to help you figure out what IMFs are involved. So these are your IMFs here.
And when it says induced dipole, it's the temporary one?
Yeah, it's temporarily inducing it. And then large biological molecules, we already kind of hit on those when we were talking about fats. All right, not technically IMFs. These are going to be your ionic, okay? That's relationship between a metal and a non-metal. They're going to be losing or gaining electrons. Metallic then is between metal atoms. It can be just for one type of metal, a pure substance, or different types of metals or alloys. And then we've got covalent network. Covalent network are going to occur between carbon atoms, silicon atoms, carbon and oxygen, silicon with oxygen. The attraction is due to multiple covalent bonds. Diamond is an example of this too. Is that on here? Did I spell that right? Okay. DIA. There we go. IMFs are strong, and they're stronger when there's more covalent bonds formed. All right, so we'll talk about miscibility, vapor pressure, surface tension, capillary action, and the results of these tomorrow, but I still want this I do, I want the we do, and I want 3-1 done by tomorrow. You don't need the rest of this lecture to do the rest of 3-1. Okay, good. Any questions? I am out of time.